I am Anil Kumar. Welcome to a very important video on trigonometry, where we are discussing strategies to simplify expressions, to prove identities, and even solve equations. The fundamental identities will be worked on to understand all these strategies. In case you want to learn from me, you can always join my classes by sending an email on the address given. Now, let us enjoy the journey of success. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll discuss test type questions based on fundamental identities. We have taken variety of test questions to give you a good experience. Let us now explore these questions one by one. So these are based on trigonometric identities. We have questions which have factor expressions, simplify expressions, verify identities, solve equations, and we'll also use inverse ratios as challenge test questions. Well, as far as trigonometric identities are concerned, you know three of them. These are the fundamental identities. Sine square theta plus cos square theta is 1. 1 plus tan square theta is secant square theta. And 1 plus cot square theta is cosecant square theta. Now, based on this, let us go through the questions. Here is our first question. You can always pause the video, answer the question, and then move on to the second one. So we need to factor each expression. Factoring is kind of important to solve equations. It is always one of the important parts to solve any equation in trigonometry especially. So we are going with primary trigonometric ratios and both secondary trigonometric ratios as shown here. Then question number 3 and 4. Again, factor and simplify. Now these, you must have seen them in some identities also. So these expressions could be part of equations and identities. So solving them really helps to master the techniques. Question number 5 and 6. We have given you the factored form. You may multiply these and then simplify using the fundamental identities. Here is a perfect square, and then now you simplify it, correct? So that is getting ready for a major test. Now in this particular case, we'll look into how do we add or subtract trigonometric identities when fraction type of equations are involved. So that will give you a good practice. And remember, a plus b times a minus b is a square minus b square. That should help you to further simplify using fundamental identities. Question number 9. Here is an identity which you need to prove. Very important identity where we are going to use the fundamental identities. Question number 10. Now in this section, the later half, we are now using arc sine. So sine inverse. Sine inverse is defined in a limited period. So we have sometimes given you, like here, x is between 0 to pi by 2. So we are considering a right angle triangle. In that right angle triangle, if you have square root of 9 minus x squared, and if you substitute x equals to 3 sine theta, then how can you write this as an trigonometric expression? This expression is extremely important even in integration, where you need to do trigonometric substitution to simplify and then integrate. So based on this, we have 4 questions. So here's the first one for you. Then the next one, 5 cos sine inverse of x is equal to square root of 25 minus 25x squared. You need to prove this. So 12 and 13, similar kind for you to practice. Prove the identity as shown here for 7 sine cos inverse x equals to square root of 49 minus 49x squared. and 9 cos sine inverse equals to square root of 81 minus 81x square. Similar kinds, but just for practice. Now, recalling you for practice, we'll have many other questions which are practice questions for you. So let me just share those practice questions with you. So here is one identity. So we have a couple of identities for you to prove based on the learnings. So this is one of them. You can make a note and prove this identity. So that's the next one. So there are 4 or 5 identities which I have taken for your practice on what we just learned. Okay, so that could be good enough. So these are the identities which you could prove based on what we have just learned. Let us now begin with how do we prove the fundamental identity itself. Now there are many ways to do that. The simplest thing which I will recommend is something like this. Take a circle and on a circle take a point. So if I have a point xy with the radius r, circle centered at 0, in that case, you know that dropping a perpendicular will give you, let's say this point is Q. In that case, O to Q represents what? If this is the angle theta, then we know that O to Q is r cos theta. And P to Q is r sin theta. And therefore, any point on the circle we could also write as what? We could write as P r cos theta, r sin theta. Now clearly, if r is 1, in that case directly you are reading cosine and sine values for that angle theta, correct? And what is r equals to? R, of course, is equal to x square plus y square square root, right? I may write r square is x square plus y square. Now with that in mind, let us prove these identities one by one. So we can write as we have written there that x square plus y square is equal to r square for any point on the circle with radius r centered at origin. Now if I divide each one of them with r square, then what happens? X over r. So x is this distance and y is the height. So x over r is cos square theta and y over r is sine square theta. And r square is 1, and that is how you prove this identity. Is that clear to you? Very simple. So that is how you can easily prove the identities. Most of you know about it. Now, for the other identities, what do you have to do? Similar approach, right? So we have x square plus y square equals to r square. Now, what is tan theta? Well, in this case, you can see that tan theta is equal to y over x, right? So if I divide by x square, then we get 1 plus tan square theta equals to secant square theta. Simple as that. Similarly, we can prove the next one starting with the Pythagorean theorem. X square plus y square equals to r square. And you want cot, right, which is x over y. So now divide by y square. And what you get is 1 plus cotangent square theta equals to cosecant square theta. Sometimes in the test, you may have to prove the identity itself, right? So now let's get started. So we have our first question where you need to factor the expression. Apply the rules which you have learned, and in this case, you know the product should be minus 48, right? So we are looking for two numbers whose product, let's say p times q, is minus 4 times 12, which is minus 48. And sum of these two numbers should be plus 13. And clearly, what are those numbers? Well, 16 minus 3 gives you, right? So we could write this as 12 cos square theta plus 16 cos, let's put all of them as theta, right? Minus 3 cos theta minus 4. Now, in the first two, we can take 4 cos theta as common. So we get what? We get 3 cos theta plus 4. And we already have 3 cos theta plus 4 on the other two terms, taking minus common. So now we can factor out 3 cos theta plus 4, and we get 4 cos theta minus 1 as the other factor. So this is kind of important since it could be part of solving an equation. I could always say this is equal to 0, find your solutions. You get the idea. Right. So the next one here is cotangent square theta plus cosecant square theta minus 5. How will you factor this? Well, we have to write them in one trigonometric ratio. This is kind of important. Now, you remember the identity which we just did. 1 plus cot square theta is cosecant square theta. So you could use that. Cot square theta is cosecant square theta minus 1, right? Let me rewrite this. Is cosecant square theta minus 1. So let's put that here. So we have, this is equal to cosecant square theta minus 1 plus cosecant square theta minus 5. So in that case, you could factor this in terms of cosecant square theta. You get the idea, right? So we have 2 cosecant square theta minus 6. And you can take 2 common, and you get cosecant theta minus 3, and that is how you could factor this particular expression. The next one here is 1 plus 2 sin x cos x over sin x plus cos x, and then we have cosecant square theta minus 3 cosecant theta plus 2 over cosecant square theta minus 1. Now, the first one, which is 1 plus 2 sin x cos x, and the remainder is sin x, the denominator is sin x plus cos x. Now, here, you could use the fundamental identity. Sin square x plus cos square x is 1. See, then it becomes very simple. Let me show you. For 1, I would write this as sin square x plus cos square x. And we already have 2 sin x cos x. Denominator is sin x plus cos x, right? Now, what is the numerator? You remember what is a plus b whole square is? A plus b whole square is a square plus 2ab plus b square. Now you see here a square, and this is 2ab, and that is b square. So I could write the numerator as sin x plus cos x whole square divided by the denominator, which is sin x plus cos x. And that gives you a linear term, without denominator, right? Sin x plus cos x. You get the idea. So that is how you could simplify it. This is indeed a very important test question. The next one here, you need to have a product of 2 and sum of minus 3. So 2 times 1 can work for you. So you can write the numerator as cosecant square theta. Now, since you know how to factor, we got the two numbers, which are minus 2 and minus 1. We will write this as cosecant theta minus 1 divided by cosecant square theta minus 1 can be written as cosecant theta plus 1 times cosecant theta minus 1. And that should help you to simplify it further, correct? So we do get our answer, which is cosecant theta minus 2 over cosecant theta plus 1. So that gives you a good practice to work with both primary and trigonometric ratios and the fundamental identities involved. Now here we will practice multiplication of these factors. So you have 2 cos x plus 2 and 3 cos x minus 3. Well, 2 and 3 can be taken common. So we get what? So we get 2 cos x plus 1, and here we could take 3, and we again get cos x minus 1. So 3 times 2 is indeed 6, and cos x plus 1 times cos x minus 1 is cos x square minus 1. Now you remember, 1 minus cos square x is sin square x. So this could be written as minus 6 sin square x. Perfect. How did we get that? Once again, let's look into this identity. Sin square x plus cos square x is equal to 1. So if I bring 1 on this side and sin on the other side, what do I get? I get cos square x minus 1 is sin square x with a negative sign, right? That's what I did. Perfect. Let's look into the next one, which is 5 cos x minus 5 sin x whole square. Well, 5 square is 25. We could also write that. So we can say 25 and think about, we're taking that outside, and we are left with cos x minus sin x whole square, right? So which is cos square x minus 2 sin x cos x plus sin square x. And you know what is cos square x plus sin square x? It is 1. So we get 1 minus 2 sin x cos x. You get the idea. So that is how we could factor. Some of you can also write 2 sin x cos x as sin 2x, right? So if you know that double angle formula, we could write this as 25 1 minus sin 2x, right? But that will also work. So that is how you could actually simplify this. Here is the next one, very commonly seen in many trigonometric identities. Now, in such cases, you need to take a common denominator, which is product of cosecant x plus 1 times cosecant x minus 1, right? And then cross multiply. So you have cosecant x minus 1 minus, let's put this in bracket, cosecant x plus 1. You may or may not factor, but normally I'll recommend not to factor expand the denominator. Denominator should always be factored, right? In the numerator, what do you get? You get cosecant x minus cosecant x, which is 0, and minus 1 as minus 2. Now let us factor this. See, we get, expand this. We get cosecant square x minus 1. And what is that equal to? So we know the identity. Let me write down on this side, which is, we can write at the bottom. So which is 1 plus cot square x equals to cosecant square x. So cosecant square x minus 1 is cot square x, right? So I could write the denominator as minus 2 over cot square x, which is minus 2 tan square x. You get the idea. So I could actually simplify this to minus 2 tan square x. Do you see that? So this is very important to understand how to work with these trigonometric fundamental identities and simplify the expressions. I'd like you to do the similar operation on question number 8. So we do have secant square x minus 1 when you multiply these in the denominator. And I like you to do the numerator part, which is 1 plus cos x times secant x minus 1 minus 1 minus cos x times secant x plus 1 and see what do you get. So I'll leave this exercise for you to do. Now here is question number 1, 9, the first question to be proven for an identity. How will you do this? Well, to begin, we can start with the left hand side since it is more complicated. On the left hand side, let's take the common denominator, which is secant x plus 1 and multiply by tan x. And then we could do the numerator, which is tan square x plus secant x plus 1 whole square, right? You can actually multiply them and simplify. So here, what do we get? We get tan square x plus secant square x plus 2 secant x plus 1 over tan x secant x plus tan x. So you have this particular expression to work with. Now tan square x plus 1 is secant square x. So you could write that as one of the expressions, right? And then further simplify and see what you get. Now since the result is 2 cosecant x, it's a good idea to write all these terms in terms of sine and cosine. You get the idea, right? So you could simplify it a lot and then use sine and cosine. Perfect. So you could do that. Or find the approach which we are going to use here. So now in this case, you can clearly see that we have the expression given to you. It is always a good idea in such cases to write them as sine and cosine and then work on it, right? So you could do alternate. So you could also convert to sine and cosine and then do the needful. Perfect. So that could be your strategy in solving such questions, correct? So try this out. So one is approach which we are giving you here. So tan square x plus 1 is secant square x. So you could write this as equal to 2 secant square x plus 2 secant x over the expression which we have tan x and we have secant x plus 1. We are coming back to the same thing, right? Because as you can see here, if I take 2 secant x common, I get secant x plus 1 as one of the factors, and therefore I did not expand. Continue with previous one. And clearly this cancelled, right? And so we have 2 secant x over tan x. 2. Secant x is 1 over cos x, right? And tan x is sin x over cos x. So clearly you can see that cos x and cos x cancel, and what remains is 2 over sin x, right? Which is right hand side. You get the idea. Because there's less space here. I'm just writing here 2 over sin x, which is 2 cosecant x. Is that clear to you? So as you see, in this particular case, expanding was not required. We came back to the factored form. So this is very critical to understand that this normally is not required. Correct? But expanding and simplifying numerator is very important. So once we did that, we came to common terms which could be cancelled, and then the left hand side got simplified into the right hand side. Is that clear to you? Right? So I hope this strategy is clear. Now converting to sine and cosine could have been a bit longer and messy because we are talking about layers of fractions here. But anyway, that can definitely work, no problems. Now let's look into question number 10, which is square root of 9 minus x squared. We have to do a trigonometric substitution. It is a practice question. So we are given x is equal to 3 sine x. And we have to substitute this in 9 minus x squared. So if I do that, I get square root of 9 minus 3 sine x whole square, right? And that gives you square root of 9 minus 9 sine square x. Now, you can take 9 common and you get 1 minus sine square x. 9 square root is 3 and 1 minus sine square x is cos square x. And you get 3 cos x. Since we are working in the first quadrant, it is positive, and therefore we wrote this as 3 cos x. Do you see? That expression is equal to 3 cos x practically. With the substitution, x is 3 sin x. You get the idea. Very important substitution. Now, similar to this, we have another question, which is 5 cos sine inverse x, right? How do you show that this is equal to 25 minus 25x squared? This is kind of reverse of what we just did. So, in doing such questions, what you could do is let theta equals to sine inverse x. In that case, sine theta is equal to x. Correct? So, we could begin with the left hand side, which is 5 cos sine inverse x, which is theta. You see that. So we substituted sine inverse x with theta here. Now, we actually want a square root. So let's square and square root it. So we could get this as, what is cos square theta plus sine square theta is equal to 1, and therefore you could write cos theta as equals to 1 minus sine square theta square root. So we'll do this substitution here. So we get 5, and instead of cos theta, we can write square root of 1 minus sine square theta. Now we know sine theta is x, so this is 5 square root of 1 minus x squared. Taking 5 inside gives us 25 1 minus x squared, which is the right hand side, right? Which is square root of 25 minus 25x squared. You get the idea. So that is the reverse type of thing which we have done. Perfect. Now here are 2 practice questions for you based on the same concept. I've seen sometimes students find it slightly difficult to work with inverse trigonometric ratios, but I think that is going to give you good practice. With that, we come to an end of this particular video where we have introduced to you the application of fundamental trigonometric identities. In case you want to learn from me, you can always send an email on the address given. Feel free to contact us, write your comments and suggestions. If you like and subscribe to my videos, that would be great. Thanks for your time and all the best.